This video is going to go over hydrolysis reactions, both acid-catalyzed and base-catalyzed of esters and amides. So, base-catalyzed hydrolysis of esters results in a carboxylate and ethanol. And an alcohol. In this specific example, it's ethanol, 2 carbons, protonate that. So we get a carboxylate and ethanol. And we could argue that some sodium is floating around by that carboxylate. Positive and negative attract. So starting right in with the mechanism, we're going to have this hydroxide attack the carbonyl carbon. One of those carbon-oxygen double bonds is going to break, giving us this. So then we still have the remainder of our original ester. Then we're going to reform our carbonyl, kick out this ethoxy group, and these are all equilibrium steps, as I should point out, so they should be drawn that way. And then this ethoxide is actually going to take this hydrogen proton, I should say, off the carboxylic acid. So then our products are the carboxylate, and again we could argue the sodium is there, and ethanol. Cool. Now acid-catalyzed hydrolysis is a little bit more complicated. So if you need to kind of watch the mechanism happen first and then write it down, or just anything that you need to do, it is long, so I will say that right off the bat. But since we have acid, so I should point out really quick, our acid-catalyzed products, well, let's write those first. Acid-catalyzed products are a carboxylic acid and ethanol. Now, carboxylic acid and ethanol, obviously, since this is acid catalyzed, we have protons more abundantly, so we're going to have obviously the protonated form of the carboxylate. Let's draw through the mechanism. So since there's no nucleophilic atoms, what's going to happen, we're going to draw in lone pairs on that oxygen, is we're going to get an activated carbonyl. Bond's going to pop off onto the chlorine. And then we can actually have water come in and attack that carbonyl carbon nucleophilically. So as we work through, we now have a tetrahedral intermediate. Whoops. Let's actually make the bond connect. Cool. So now more water is going to come in, and I'll draw that a little bit out of the way of the. Actually, we're gonna move this up a little bit. Cool. So now some water is going to come in and deprotonate. Oh, I should draw the positive charge on now, shouldn't I? Deprotonate so that we now have another tetrahedral intermediate. But now we have 2 alcohol substituents on the same carbon. And we have this H3O plus that we generated. Now obviously, if you are in your undergraduate organic right now, and you know that we generate something like H3O plus, or some negative ion for the same argument that's going to become relevant pretty soon or eventually in the mechanism, and this in fact will, as this oxygen down here with these lone pairs, is actually going to take a proton, or get protonated as we could say, from that H3O plus, So then we still have our tetrahedral intermediate transition state looking thing. And now we can reform our carbonyl, push out some ethanol, Now, I think it's important to note, just because we're reforming the carbonyl doesn't mean that we lose this hydrogen. So it is important to draw the carbonyl activated with a positive charge. But then, as true catalysis tells us, if we start with H3O plus or some form of protons in solution, we'll end with some form of protons in solution. So some good old trusty water is going to come in, deprotonate our carbonyl, and give us a carboxylic acid and ethanol. So there are the acid-catalyzed and base-catalyzed hydrolysis mechanisms for esters. Take a minute and look at those. And now we are going to go on to amides. So hydrolysis of amides actually requires some pretty harsh conditions, and for the sake of the argument, we should be writing heat over these because it does, again, require some pretty harsh conditions. So as the products hinted at for the base-catalyzed hydrolysis of esters, the product of the amides is going to follow pretty much the same pattern. We're going to get this carboxylate product plus this part of the molecule that ends up leaving. In this case, it is ethylamine. Again, we can make the argument that sodium kind of hangs out with this carboxylate. So let's go through the mechanism again. It's really similar to base-catalyzed hydrolysis of esters. So we're going to draw in our hydroxide. Make a nice arrow. A nice arrow. Cool. There we go. So now we have our tetrahedral intermediate. We're going to reform our carbonyl, push out this soon-to-be ethylamine, so then we have this, well, let's go this way actually. Lone pair, cool. Negative charge. So now we're actually going to protonate this to form ethylamine and our carboxylate. Cool, so pretty straightforward mechanism, really similar to base-catalyzed hydrolysis of esters. So now let's go ahead and do acid-catalyzed hydrolysis of amides. Again, pointing out, look at that pattern. Obviously, in acid-catalyzed hydrolysis, we have an abundance of positive charge in solution, so H3O+. Base-catalyzed, we have the negative charge with the hydroxide. So you should expect we're going to have carboxylic acid. But this time, instead of an amine, we're actually going to have an ammonium cation. So again, in the acid-catalyzed hydrolysis, we have positive charge on the products. Base-catalyzed, we have a negative charge on the products. That's pretty straightforward. So I hope it makes sense, but let's rationalize that positive charge and the ammonium cation through this mechanism. So let's do some chemistry right now. So again, obviously nothing to act nucleophilically, so we're going to have an activation step of our carbonyl. And again, same amide, so we can kind of see how the processes are different. So again, water is going to come in. Much better. Nope, can't do it. There we go. Sorry, I'm very specific about writing things well, both so that I can read it and so that you can read it. So, my apologies for that. Sometimes it's just a touch difficult, but we've got it under wraps. Get it at the right spot. Cool. So here's our tetrahedral intermediate. Again, some good old water is going to come in and deprotonate. Now we're going to have these identical alcohol substituents. I just like to draw the OH bonds in just to kind of show what's left of what we started with, just so it's a little bit more clear. So again, that H3O plus doesn't stick around for long. Gets taken care of by this lone pair on the nitrogen. Takes a proton right off. Actually, I'm going to move those arrows down just a little bit so we can see what we're doing and not run into other parts of the reaction. So now we have this. Someday. So now we have this intermediate again. Here we go now. We will reform our carbonyl, punch out some ethylamine while we're at it. Now remember, this is an activated carbonyl, so you don't lose that hydrogen just because it would be convenient. You do have to figure out something that's going to happen to that, but as I've told you, lone pair on this nitrogen is going to steal this proton, thus giving us our final product of our carboxylic acid. And we'll make those lone pairs a little bit better. Plus and we'll make this hydrogen a little bit better connected. There we go. This ammonium cation. So there you have it. Acid catalyzed and base catalyzed hydrolysis of both amides and esters. I hope seeing it all together helped you see the relationships and that the mechanisms help rationalize those products for you. We'll see you next time.